Now that we've looked at the dimensional changes, let's actually start calculating out the stress. One thing to keep in mind though, just like everything that we've done in the course of this class, is we're going to have to assume that we're dealing with a linear elastic material. And let me change the color of my thing. So we've got a linear elastic material. Not only do we have a linear elastic material, but we're going to be assuming that we're in the elastic range. So we're not applying enough force to permanently change the makeup of the bar itself. We're applying just enough force that when we let go, it will all spring back. And so given that, we know that Hooke's law states the stress is going to be equal to, oops, sorry, I was swiping a piece of dirt off there and it went away. But the normal stress is going to be equal to modulus of elasticity times the strain. And so we had just in the previous video said that, okay, well, I know the strain is going to be a combination of, oops, it's a C, a combination of negative y over c times what the maximum strain is, times the modulus of elasticity. I don't think my computer wants me creating videos right now because it's doing all this weird stuff. And so then if I look at that, well, if I got the maximum strain times the modulus of elasticity, well, I can say that's negative y over c. Well, that's going to be the maximum stress. So once again, we're in a situation where we can sit there and look at it, and we could calculate out what the stress is if we know the geometry and what the maximum stress is. Now, the important thing with this, though, to look at is we can see the stress is going to vary linearly. So a straight line, just like our strain. So that shouldn't surprise us. Now let's go over and look at a picture here. So this is what the bending stress would look like. Now, this is a case of where I am bending the bar up, so I'm making a smiley face out of it, because what's going on is it's compressing at the top. Since it's compressing at the top, it's a compressive stress, and it's elongating at the bottom. So, by definition, the resultant force above the neutral axis has to equal the resultant force below. So if we sit there and go, well, because these are force distributions, they're force densities, and so, and the reason I say by definition is because of static equilibrium, they're going to have to equal out. So if I look at this, and I look at each one of these individual little forces, then I can say, well, dF, the differential element of force, is going to be equal to stress, which is our force density, times a differential element of area. So if I sum all of these forces together, they end up having to equal 0. Okay, so that tells me that 0 is going to be equal to the integration over the area of all the forces. And so now if I look at that, well, I know that the force is the stress times the differential area, so integration of the stress over the area. And we've been making this assumption that we're in the linear elastic region, so what we can say is, okay, we're going to integrate over the area of the definition of our stress. So y over c times the maximum stress over that whole area. And so let's pull the constants out, and the constants are things that are not going to change with the area. So stress max isn't going to change with the area. Stress max is always going to be the stress max. Same thing with the neutral axis, because that's not going to change. So I can pull those out because they're not going to vary with the area. So negative stress max over c, and then we're going to integrate y over the area. Now, we've said this all has to equal 0. So now if we look at this, a couple things to note. Well, first, that first term of stress max over c isn't going to be 0 because that would be a trivial solution and nothing really exists. So since it cannot equal 0, that tells us that as I integrate y over dA, that entire thing needs to be 0. So since that part has to be 0, what does that tell us? Well, this is the first moment of inertia of the cross-sectional area about the neutral axis, because this is all around the neutral axis. And since that must be 0, that can only happen in one situation and one situation only. And that tells us that our neutral axis, which I'm going to abbreviate NA, has to also be the exact same as our centroid axis. Because if you remember, that is the definition of our centroid. Why do I care? Well, why is this an important revelation? Because now, up until now, we haven't talked about, we've said, okay, the neutral axis is this thing that doesn't change, but we really hadn't talked about how you could get it. Well, now we can solve it, because we can sit there and go, this is where my centroid is, which means this is where my neutral axis is. And that's great. So, how do we calculate our centroid? Well, we just go to our mechanics and static stuff. So how do we calculate out where the centroid axis is? Well, I can go to my equation manual and take a look at that. And that'd be great for squares, rectangles, circles, simple shapes. But obviously, we're going to be doing complex shapes. We're going to be doing I-beams and stuff. So we have to calculate it out from mechanics. So let's remind you, y bar, so this is my distance to my centroid. How do we calculate that out? Well, we sit there and we're going to have to do the sum of the y-dAs of each individual shape, and then divide it by the integration of the area. So the way that we accomplish that is we sum up the y bar a's of each individual area piece, and then we divide it by the sum of the area. So this is something, if you can't remember exactly how to do it, check your mechanics notes, or if you need to, let me know and we'll do an example or something. So that's the important thing to take away here. Centroidal axis is going to be our neutral axis, and we'll be able to calculate things based off that.